Dear learners, I am Gaurav Kumar Agrawal, working as Assistant Professor at UTD CSVT Bhilai. In today's session, we are advancing to the topic of Foundation, Shallow Foundation. Part 1. Shallow foundations are a crucial element in structural engineering, providing the necessary support to transfer the building loads to the soil. We will explore the different type of shallow foundations such as spread footing, strip footings, padded footings, combined foundations and discuss their applications. By the end of this session, you will gain a solid understanding of shallow foundations and be prepared to apply this knowledge to the real world construction projects, ensuring stability and safety. We will discuss the following key points. First, introduction, then the depth of footing, then strip footings, then isolated footings, then grillage foundations and at the last combined footings. So, what are different type of foundations? Foundations are a critical component in any construction project, serving as the structural base that transfers the load of a building to the ground. Broadly, foundations can be classified into two different primary types. First is shallow foundations, second is deep foundation. So, what is shallow foundations? According to Terjazis, a foundation is classified as shallow if its depth is equal to or less than its width. These foundations are also known as open foundations because they are constructed through open excavation. Even foundations that are deeper than their width but constructed via open excavation fall under the category of shallow foundations. These foundations are situated immediately below the lowest part of the superstructure they support. The term footing is commonly used in the context of shallow foundations. A footing is a foundational unit built from the material such as brickwork, masonry or concrete, located under the base of a wall or column to distribute the load over a larger area. From a design perspective, footings can be classified into four types. First is spread footing, second is combined footing, third is strap footing and last is mat or raft foundations. Spread footings. This type of footings supports either a single wall or column. It can be further divided into two subtypes. First is strip footing, a spread footing designed for walls, and second is pad footings and isolated footings intended for columns. When a spread footing supports more than one column or wall, it is referred to as combined footing or strap footing. A mat foundation, also known as a raft foundation, is a continuous foundation unit in two directions, covering an area equal to or greater than the building's base area. The next is depth of footings. Determining the appropriate depth for footings is essential for ensuring the stability and longevity of a structure. Footings should extend below the top organic soil, miscellaneous fill, abandoned foundations, debris or muck. If the top loose soil or fill is excessively deep, two alternatives may be considered based on economic factors and time availability. First is removing and replacing soil. The top soil directly beneath the footing can be removed and replaced with lean concrete. This approach provides a stable base for the footing. And the second is compacted sand and gravel fill. Alternatively, the top soil can be removed over an area larger than the footing and replaced with compacted sand and gravel fill. This fill must be sufficiently large to distribute the footing load effectively. In both the cases, it is crucial to reach a stratum that possesses the required bearing capacity for the good footing foundation design. Sometimes the topsoil may be good, compact and possesses adequate bearing capacity. In such cases, it is desirable to keep the minimum depth of the foundation as given by Rankine's equation, that is d minimum is equal to q by gamma multiplied by 1 minus sin phi divided by 1 plus sin phi to the whole square, where phi is the angle of repose with values that can be referenced from standard tables, and q is the intensity of the load at the base of the footing in kilonewton per meter square. Gamma is the unit weight of soil in kilonewton per meter cube. The depth of the footing should also ensure that the rate or angle of load spread from a wall base to the outer edge of the ground bearing does not exceed permissible values. This consideration is crucial for maintaining the structural integrity of the footing. The National Building Code of India, that is SP 7/2005, provides specific recommendations regarding the depth of foundations. First is ensure that the foundation reaches adequate bearing capacity. Second is consider the depth of shrinkage and swelling in clay soils due to seasonal changes, which can cause significant movements. Take into account the depth of frost penetration in fine sand and silts. All the foundations should extend to a depth of at least 50 cm below the natural ground level. On rock or other weather resistant natural ground, removing the topsoil may be enough. If the subsoil conditions adjacent to the construction site impair the stability of the building, the foundations should extend beyond these detrimental influences or be shielded from them through appropriate measures. The next is strip footings. A strip footing provides continuous longitudinal bearing and is typically used for supporting walls. Strip footing can be designed in two main ways. First is simple strip footings without masonry offset. For walls carrying light loads or when the shape bearing pressure is high, a simple strip footing is often sufficient. In such a cases, the concrete base projects slightly beyond the wall face. The width of the concrete base should be at least twice the width of the wall, and its thickness should be equal to the projection for cement concrete or 1.5 times the projection for lime concrete. The next is strip footings with masonry offsets. For heavier loads or lower shape bearing pressures, the base width required will be significantly larger. Masonry offsets are used to achieve a larger spread before the load is transferred to the concrete base. The height and width of each offset should be proportioned to ensure that the load spread rate does not exceed permissible values. The National Building Code of India specifies that the load spread angle from the wall base to the ground edge should not exceed a ratio of n1:1, where n1 is horizontal and 1 is vertical, where n1 is equal to 2/3 for lime concrete and n is equal to 1 for cement concrete. The next is isolated footings or pad footings. And isolated footings or pad footings supports a single column. The base area A of such footings is calculated using the equation A is equal to P divided by Qs, where P is the total load transmitted by the column including the footing load, and Qs is the shape bearing pressure or capacity of the soil. So, in the padded type of footing, first is simple pad footings. Simple pad footings are used when the structural load is relatively small or the ground has a high shape bearing capacity requiring a smaller base area. In such a scenarios, the footing can be a simple concrete block which extends equally from a column face on all the sides, creating a uniform projection. Its key feature include: first is footing shape and size. The shape of the footing generally matches the shape of the column. This could be trapezoidal, square or circular depending on the column's cross section. The objective is to ensure equal projection on all the sides of the column, which means the footing's base area is symmetrical relative to the column's footprint. The next feature is projection and extension. The column base should extend outward from a column face by a distance at least twice the lateral dimension of the column in all the directions. This ensures that the load is adequately spread over a larger area of the soil. Then the next is thickness of the footing. The thickness of the concrete block forming the footing is determined based on the material used. For cement concrete, the thickness should be equal to the projection of the footing. For lime concrete, the thickness should be 1.5 times the projection. This variation is due to the differing load bearing properties of cement concrete and lime concrete. Load spread angle. The load from the column spreads out through the footing at a certain angle. This angle should not exceed a certain ratio. For lime concrete, the load spread angle should not exceed a ratio of 2/3:1, that is height to horizontal distance ratio. For cement concrete, the load spread angle should not exceed a ratio of 1:1. This means that for every unit of height in the footing, the load can spread horizontally by up to 1 unit for cement concrete and up to 2/3 of a unit for lime concrete. Then the next is stepped pad footing. Stepped pad footings are employed when dealing with larger structural loads or when the shape bearing pressures or capacity of the soil is relatively low. Under these conditions, a larger base area is required to adequately distribute the load from the structure to the ground. To achieve this, larger base masonry offsets or steps are introduced. Its key feature includes masonry offsets. Masonry offsets are horizontal steps that extend outward from the base of the column or pillar. These steps progressively increase the area of the footing, allowing the load to spread over a wider area before being transferred to the underlying concrete base. The design of this offset is crucial. Each step must be carefully proportioned in height and width to ensure the rate at which the load spreads does not exceed the permissible values, which are governed by the material properties and soil conditions. Then the next is offset dimensions. The allowable dimensions for the offset vary depending on the type of pillar. Like for brick pillars, the offsets should not exceed 5 cm. These limitations ensures that the load spread is controlled and remains within the safe limits for the material. For masonry pillars, the offset can range from 10 cm to 15 cm, offering greater flexibility in the design due to the material's higher strength and stability. These dimensions help in evenly distributing the load across the stepped footing, preventing any potential structural failures due to excessive load concentrations. Then the next is step heights. The height of each step in the footing is another critical parameter. It should be between 15 cm to 22.5 cm. This range allows for a gradual and controlled spread of the load as it transfers from the structure to the footing and eventually to the ground. Properly proportioned step heights ensure that the footing remains stable under the applied loads and that the load is efficiently distributed across the entire base area. Its application include stepped pad footings are commonly used in situations where the load is substantial or the soil's bearing capacity is not sufficient to support the structure with a simple pad footing. The stepped design allows for a larger footing area without requiring an excessively deep or thick concrete base, making it a practical and efficient solution in many construction scenarios. Then the next is sloped padded footings. A sloped padded footings, also known as a sloped or tapered footing, is a type of foundation element where the thickness of the footing varies along its length, typically increasing towards the column or load bearing structure. This design is used to efficiently transfer the load from a structure above to the ground below while minimizing the amount of concrete required. Then the next is footings for reinforced concrete columns. Reinforced concrete columns require robust and specifically designed footings to adequately support the loads transferred from the superstructure. These footings are a crucial component in ensuring the overall stability and safety of the structure. Its key feature include: first is reinforced concrete footings. The footings supporting reinforced concrete columns are themselves made of reinforced concrete. This material choice is essential due to the need for the footing to bear the significant loads that the column transmit and to resist the forces acting upon it without failing. Structural integrity. The design of the footing must ensure that both the column and the footing maintain their structural integrity under all loading conditions. This involves considering various factors such as load distribution, soil bearing capacity, and the interaction between the column and the footing. The reinforcement within the footing is designed to handle tensile stresses that occur due to bending moments and shear forces. Proper placement and detailing of the reinforcement bars are crucial to prevent cracks and structural failure. Design considerations. Design footings for reinforced concrete columns involves detailed calculations and considerations to ensure that the footing can safely distribute the loads to the underlying soil or rock. This includes assessing the bearing capacities, footing thickness, reinforcement layout, and ensuring that the footing is adequately anchored to resist uplift or sliding forces. The shape and size of the footing are determined based on the column's load, soil conditions, and any additional forces or moments that may be applied to the structure. The footing is typically rectangular or square to match the column shape, but may also be circular or of any other form depending on the shape of the designing requirement. Next is eccentrically loaded footings. Typically, footings are designed so that the center of gravity of the superimposed load coincides with the center of gravity of the base area. This design ensures that the footing experiences concentric loading, resulting in uniform bearing pressures. However, in certain situations, it may not be possible to achieve this alignment. For instance, when a wall or a column is constructed near another property, it may not be feasible to spread the footing equally on both the sides of the column or the wall. In such a cases, the footing is subjected to eccentric loading, which requires special design considerations to ensure stability and uniform load distribution. Then the next is grillage foundations. Grillage foundations are a special type of isolated footing used primarily for heavily loaded steel stanchions, particularly in locations where the bearing capacity of the soil is poor. The depth of these footings is typically limited to between 1 and 1.5 meter. The load from the column or stanchion is distributed over a large area through layers or tiers of joist, with each tier placed at right angles to one below it. Grillage foundations are classified into two types. First is steel grillage foundation, second is timber grillage foundation. First is steel grillage foundation. A steel grillage foundation is a type of foundation that uses steel joist or beams arranged in multiple tiers or layers to distribute heavy loads over a larger area. These joists are typically placed perpendicular to each other, forming a grid or grillage which helps spread the load from the structure above to the underlying soil. Steel grillage foundations are commonly used for structures that exert significant loads, such as columns supporting large industrial buildings or heavy machinery. The steel joists are often encased in concrete to protect them from corrosion and to provide additional stability. Next is timber grillage foundation. A timber grillage foundation operates on a similar principle to the steel grillage foundation, but uses timber joist instead of steel. These timber joists are also arranged in layers, forming a grid that helps distribute the load over a wider area. Timber grillage foundations are typically used in lighter structures or in areas where timber is readily available and cost effective. They are often employed in temporary structures or in areas with relatively good soil conditions, as timber is less durable than steel and more susceptible to decay over the time. Then the next is combined footing. Combined footings are structural foundations designed to support two or more columns when individual footings are not feasible. This situation typically arises due to spatial constraints, overlapping loads, or soil conditions that requires a more extensive base area for adequate support. The main purpose of a combined footing is to distribute the loads from multiple columns onto a larger footing area, ensuring structural stability and preventing excessive settlement. Situations that requires combined footings include: first is close proximity of columns. When columns are positioned very close to each other, their individual footings might overlap, making it impractical to construct separate footings. A combined footing addresses this issue by providing a single unified foundation that supports both columns effectively. Second is low soil bearing capacity. In cases where the soil's bearing capacity is insufficient to support the loads from individual columns, a larger footing area is required. A combined footing allows for this increased area, distributing the loads more evenly across the weaker soil, thereby reducing the risk of differential settlement. Third is property line constraints. When a column is located near a property line, the available space for the footing is spread may be restricted on one side. A combined footing in such a cases enables the load distributed within the limited space, ensuring that the structural integrity of the building is maintained while respecting property boundaries. Then what are the various types of combined footings? Combined footings can be broadly classified based on their shape and the number of columns they support in the following types. First is rectangular footings. A combined rectangular footing is used when the loads from two columns are relatively similar. The footing's dimension, that is length and width, are carefully chosen to ensure that the center of gravity of the footing aligns with the center of gravity of the loads from the column. This alignment is critical to maintaining uniform pressure distribution under the footing, which helps in minimizing differential settlement and ensuring that the structural stability of the building. Next is trapezoidal footing. A trapezoidal footing is utilized when the columns supported by the footing carry unequal loads. This is often the case when one of the column, particularly the one closer to a property line, carries a heavier load. The trapezoidal shape of the footing allows for the center of gravity of the footing to align with the combined center of gravity of the column loads, even when the space is restricted on one side. This alignment is essential to maintain balance and ensures that the load distribution is uniform across the footing. Then the next is combined rectangular footing. A combined rectangular footing is specifically designed to support two columns by ensuring that the center of gravity of the footing aligns perfectly with the center of gravity of the loads from the columns. This alignment is achieved by carefully selecting the dimensions of the footing, its length and width, so that the pressure distribution under the footing remains uniform. The structural analysis and design of this type of footing consider the net upward pressure from the soil, which is a crucial factor in ensuring the footing's stability. These footings are typically constructed using either reinforced cement concrete or steel grillage depending on the specific requirement of the structure. So, first is reinforced cement concrete. RCC combined rectangular footings are reinforced with steel bars to resist bending stresses both longitudinally and transversely. This reinforcement is crucial for maintaining the structural integrity of the footing, especially in situations where the loads are substantial or the soil conditions are less than the ideal. The reinforced concrete slab used in the condition is designed to distribute the loads evenly across its area, preventing excessive settlement and ensuring that the columns remain stable under load. Next is steel grillage. Steel grillage combined rectangular footings utilize a series of steel joists arranged in layers to distribute the load from the column to the soil. The steel grillage system is particularly effective in situations where the loads are heavy, as the steel joist can be designed to carry substantial loads while minimizing the footprint of the footing. The upper tier of steel joist directly receives the load from the column and transfers them to the lower tier, which then distributes the load to the soil. Then the next is RCC combined rectangular footing. And RCC combined rectangular footing is a type of foundation that consists of a reinforced concrete slab which is designed to resist bending in both longitudinal and transverse direction. The reinforcement within the concrete slab is placed to ensure that the footing can withstand the loads imposed by the columns as well as the pressure from the soil below. Its design considerations include the thickness of the concrete slab is determined based on the load it needs to support and the bearing capacity of the soil. In cases where the distance between the columns is large, the design may include a longitudinal beam that connects the column, providing additional support and reducing the risk of excessive bending or shear in the footing. This longitudinal beam can be placed either below the footing slab or projecting above it, depending on the specific design requirements and the overall structural layout of the building. Next is steel grillage combined rectangular footing. A steel grillage combined rectangular footing is designed to support two steel stanchions using a grillage system of steel joist. This type of footing is particularly effective for supporting heavy steel structures where the loads from the columns need to be distributed over a larger area to prevent excessive settlements. Its grillage system include: the grillage system consists of two tiers of steel joist. The upper tier directly receives the load from the columns, while the lower tier transfers these loads to the underlying soil. The joists in the upper tier are typically shorter and designed to carry the direct load from the columns, whereas the joists in the lower tier are longer and spaced further apart to distribute the load evenly over the footing area. This arrangement ensures that the load is spread over a larger area, reducing the pressure on the soil and minimizing the risk of settlement. Then the next is combined trapezoidal footing. A combined trapezoidal footing is used in situations where the two columns it supports carry unequal loads, particularly when the outer column near the property line carries a heavier load. This type of footing is essential in scenarios where the space is limited, as the trapezoidal shape allows for the center of gravity to align with the center of gravity of the combined load even when space is constrained on one side. The trapezoidal shape of the footing ensures that the heavier load near the property line is adequately supported while the overall pressure distribution remains uniform across the footing. This design helps prevent tilting or uneven settlement which could compromise the structural integrity of the building. The dimensions of the trapezoidal footings are carefully calculated to ensure that the load is distributed evenly, taking into account the differences in the loads carried by the two columns. RCC combined trapezoidal footing. An RCC combined trapezoidal footing is similar in design to the rectangular footing, but is specifically used when the loads on the two columns are unequal. The reinforcement within the concrete slab is designed to resist bending stresses in both longitudinal and transverse directions, ensuring that the footing remains stable under load. Then the next is steel grillage combined trapezoidal footing. A steel grillage combined trapezoidal footing is designed to support two steel stanchions using a grillage system of steel joist. This type of footing is particularly effective in situations where the columns carry unequal loads, with the outer column near a property line carrying heavier loads. Then the next is continuous footing. A continuous type of footing is used to support more than two columns and is analogous to a strip footing used for walls. This type of footing provides continuous support along the length of the structure, ensuring that the loads from each column are transferred to the footing slab in a uniform manner. Dear learners, we have reached the end of today's session. I hope you found it informative and engaging. Thank you for your attention. See you in the next class. Thank you.